My project title name is Cool Kubernetes. This is because I really appreciate how cool Kubernetes is. So let me give you an idea where I got the motivation to do project. So when I was at home, I was watching Paris Olympics, and this is the viewer count. As you can see, 4.8 crores during the peak time, and later in the night it was 21 lakhs. So what actually made me curious is how does a backend scale up or down to manage the user load, and the important of it for cost cutting. So the tool which I'm using for this experiment is Kubernetes to create a local cluster with single node. I'm using Docker desktop. The next tool I'm using is Kubernetes dashboard. It will basically show the total number of live pods along with the CPU and memory usage. For doing the stress test, we are using another tool called as Locust. So basically this will create load and we'll see if our application is scaling correctly or not. It also shows how our application is responding to the number of requests increasing. So the first approach here is monolithic architecture. So basically what do we do is we package all of our application into one single pod. But the major drawback over here is as the load increases on our application or even at a single endpoint, let's say service A, our Kubernetes would basically scale up the full application if the load increases. And so basically to create a dummy server, I'm using Express and Node.js. As you can see in this code, I have defined three endpoints. This is the base URL, and this is the service A and service B. And I have also added some delay over here to make it look real. As we are using a monolithic architecture, we are packaging all of the application in a single Docker container. After building the Docker image, I'm pushing it to the Docker hub. So basically for my Kubernetes cluster, I'll have to give it some configuration file. So here is the first deployment file in which basically I tell what my single pod should look like. Here I'm telling it where to look for the image. This is the image on Docker hub which we have built earlier. Then here I'm allocating it resources. This is the minimum number of resources it will get. 1000 M means one core, one CPU core. So 100 M means 10% of a CPU core. I'm also limiting it to 500 M because I don't want a single pod to throttle my computer or take my resources. Then later in the HPA file, we define how our application should scale up or down depending on the load. I'm giving it minimum 3 replicas and maximum 15 replicas. As you can see, if the resources like memory or CPU, either of it, if the average utilization increases greater than 40%, then it will spin up more containers. But if after 30 seconds, if the load decreases, then it will scale it down. Then in the service file, basically we are defining an external load balancer service. This will evenly distribute the load amongst the pod. So basically it does not overwhelm a particular pod, and the average delay is reduced, improving the performance. I've already applied the configuration file to my Kubernetes application. As you can see, we have 3 pods currently running, and also here the current utilization which is 0 because we haven't started the load test. Now this is the dashboard. You can also see over here the utilization. If I go in the browser and load, you can see our application. Now let me go to Locust and start the load test. You can see it has already started to do it. As you can see over here in the dashboard, the utilization of pod has started to go up. Now the load balancer will actually make sure that the load is distributed among these pods equally. So the average response time is still low. As you can see, the average utilization shot up to 156 percentage. As you can see, we have all the 14 pods up and running. We still have a 0% failure rate. As you can see, even after spinning up more containers, the average utilization was still 75%. Yeah, as you can see, we have all the 15 pods up and running. As you can see, the utilization of the new pods is reduced, but the old pods are still trying their best. Yeah, as you can see over here, we have all 15 of the pods, but still the average utilization is greater than 52%, but it won't spin up more containers because we have capped it. Now let me stop the test. Now as soon as I stop the test, our containers will our application will start to scale down. uh, as you can see in this graph, how we ramped up our users and kept it at 10,000 concurrent requests per second. But you can also see our response time is constant throughout the experiment, and here is the moment where we stop the experiment. And also we are always having zero failures. As you can see, we have already started to terminate some containers. Yeah, in this also you can see started to terminate all the pods. As you can see here, our application has started to scale down as the load is decreased. Also on the dashboard, you can see how the usage went down. As you can see, we are back to 3 pods. Load initially was 0% and we only had 3 replicas, and then once we started the load test, the CPU utilization shot up, and then we just spun up more containers. We stopped the stress test, Kubernetes decided to spin down the containers, and now we are back to 3 replicas. Now here the second approach we are going forward with is microservice architecture. In this, basically we are giving a individual pod for a particular service. Here service A and B are represented by blue and red color pod respectively. Now let's say the load increases on service B pod. So basically our Kubernetes will create replicas for that particular pod slash service only, which proves to be more cost effective rather than scaling the whole application as we saw before. Here we are setting up a proxy server which would basically intercept the request and then redirect it to the correct pod A or B depending on the request. This proxy server also acts as a load balancer which will distribute the load among the pod. So basically this avoids overwhelming any particular pod and improving the efficiency. As you saw in the first approach, how all of the services in monolithic architecture are tightly coupled together and all of them work on a single Express server. But what do we do in the microservices architecture is give each service its own Express server running on a different internal port, and then there is an proxy server which would basically forward the request to the appropriate service A or B. And also you can see how the directory structure here looks like. This is here where the proxy server is, this is service A server, and this is service B server, and then proxy server would transfer the request to service A server or service B server internally. What do we do is we are going to dockerize all of the server, proxy server, service A server and service B server, and the images have been pushed on the Docker Hub. So these are our Kubernetes configuration file. This is the proxy server deployment file. So this is also going to act as a load balancer. Also keep in mind that this proxy server is not going to scale. There's always going to be one replica. Therefore we want this to have enough resources. And this is a service A deployment file, and this is a service B file respectively. This is our HPA file. This will tell Kubernetes how to scale our pods. So we are basically keeping minimum 2 replicas for each service and maximum 5, and it would scale up if the average utilization is greater than 40% and scale down after the stabilization window of 5 seconds has passed. Now as you can see on the Kubernetes dashboard, we have total 5 pods, where proxy server has one replica, service A and B both have 2 replicas each. This is the memory and CPU utilization you can see in here. Now let me go and start a stress test at service B API endpoint. Current users and ramp up 50 users per. As you can see here, after the load test on service B, its CPU utilization shot up, and then Kubernetes started to create replicas for pod B. As you can see in here, all the 5 replica for service B pod have been created by Kubernetes, and the average CPU utilization went down. If I go and show you on the dashboard, all 5 pod of service B have been created, whereas service A only has 2 out of 2 pods alive, because only load on service B because there was a load only on service B, indicating how computationally microservices is effective. Now let me go and stop the loading test. As you can see, the CPU utilization went down to 0% because we have stopped the loading test. As you can see, Kubernetes has started to terminate the extra replicas of the pod B which it created. Uh, as you can see, now we are back to the original state where we started. Back to the dashboard. As you can see, now we are back to the original state we started and only have 2 pods. This shows how effective microservice architecture is. When load on a particular service increases, only that particular pod is replicated and not the whole application. Now if I go to the report which is generated by Locust, as you can see here how the number of requests were throughout the experiment, and we had 0 failure rate always. This is the response time, which is constant throughout the experiment, indicating how effective our system handled the load.